Okay, we are going to start the session. I believe I'm audible. Good evening, everyone gathered here. I'm your host, Devanandan MB, and today we'll be taking an introductory session to cryptography. This is part one of the two sessions that we're going to take on cryptography. The agenda for today is that we'll give you guys a basic idea of the terminologies associated with cryptography. We'll be exploring some classical ciphers like Caesar cipher, Ignia cipher, and stuff. Am I audible? Okay, so now we'll be exploring some classical cryptographical systems such as Caesar cipher, Ignia cipher, or 13, and some fundamental theorems of cryptography, some basic stuff like modular arithmetic. In the next session, we'll be covering into more modern cryptography like RSA, other topics. Okay, so let's start. What is encryption? Cryptography primarily deals with encryption of data. Encryption is a process of converting data into an obscure form so that unintended parties have no access. Basically, you have a data and you need to transform this data such that only people who possess the key can decrypt it and get it back to its original form. One of the primary requirements of an encryption process is that you should know how the encryption is done. Basically, you should have access to the process, but still not be able to decrypt without, unless you have the key. Okay, so we'll start off with a few terminologies associated with cryptography. When we talk about cryptography, what comes to your mind first? Considering that most of my intended audience is the high school students, first thing, what you guys might be guessing first will be steganography. Steganography is the art of hiding data within another data. Its intended purpose is to hide data from adversaries, and to do that, you will take the data and you will encode it into another piece of information, which you can decode only if you know how you did them. Steganography is different from encoding and encryption. What is encryption? Encryption is meant to hide data from unintended parties by transforming the data through a set operation and a key. So you have an algorithm. You take the data, you give this data to the algorithm and pass the key onto it, and this algorithm will turn this data into some cryptic message. Now, encryption is a one-way process unless you have the key. Like as I said, you can't decrypt a message unless you have the key. That is encryption. What is encoding? Encoding is completely different from encryption and steganography. The purpose of encoding is not to hide data. Its purpose is only to transform the data into another format. Say, for example, we have a web service which takes in data which is only ASCII characters, printable ASCII characters. But suppose our data is not printable ASCII characters. We want to pass the data, but it should be in while passing on the data, it should be in a format such that it is completely printable. So we can take our data, we can transform it, encode it into just ASCII characters and give it to the server, and the server could decode and work with the actual data. So encoding is meant for transforming data so that it can be properly and safely consumed by a different kind of system. Encoding was never meant to be encryption. So if you are given an encoded data, you could always convert it back with variously. There's no notion of key within encode. Okay, so now we shall look into some classical crypto systems. These were used in the bygone era, the era of great Caesar, the era of centuries past, to like pass or like hand over. Okay, so now we'll be looking into some classical crypto systems. These systems were used in the bygone era to pass on information secretly to, say, emperors and kings. At that time, information is of critical value. Like a king might be expecting a war. Like a messenger might be sending to a king the information about a war, and if an adversary finds about it, he could thwart all defense systems. So, and like ciphers of these were of paramount importance at that time. Before we move on to classical crypto systems, we'll look at modular arithmetic, because we'll be needing modular arithmetic to work, implement and understand some of these classical crypto systems. So, modular arithmetic deals with a finite set of elements, and we'll have a few operations defined on them. Let's take an example. You guys can see the clock on the right side of this slide, right? You have the numbers from 1 to 12 on. So suppose it's 10 o'clock and you go 3 hours past 10 o'clock, you will be reaching 1 o'clock, right? So we can model this system into a modular arithmetic concept. Say the modulus in this case would be 12. So, the modulus in this case will be 12. Let's take an example. Let's say it is 1 o'clock at the moment. So, it is the element is 1, and if you're going to add 3 to it, say you go 3 hours past 1 o'clock, what would you get? You'd get 4. Okay, fine. Now let's take a special case. Let's say it is 11 o'clock right now. Let's go 2 hours past 11 o'clock. What would you get? Not 13 but 1. Why? Because we are taking the remainder of 11 plus 2 modulo 12. 12 is the modulus in this case. So, right. This notion of modular arithmetic is very important when it comes to cryptography. We'll see why that is in a moment. Before we move on, there are two operations within modular arithmetic. One is addition and one is multiplication. Okay. Let's see how. Let's now look into Caesar cipher. Caesar cipher, named after the great Julius Caesar, is a very basic cipher. So to encrypt a message, to encipher a message in Caesar cipher, you take the plain text and you'd apply a shift to each of the characters of the plain text in the message. Let's take this example, hello world. Okay. The first character in this plain text is H, and you'd apply a shift to it. When I say apply a shift, I mean, like say for example, we are applying a shift of 2 to A. A shifted to 1 would be B, and B shifted by 1 would be C. So a shift of 2 on A is C. Okay, clear? Alright. So we'll apply a shift of 13 to H, you'll get U. Similarly, you apply the same shift to each and every character in the plain text to get the final ciphertext string. Right? Right. So this is a breakdown of how it works. We have the plain text here, attack. The shift here is 7. The shift is also the key for the cipher. Okay. So A shifted by 7 would be H. T shifted by 7 would be A. T like similarly, and for each of the characters in plain text, you'll shift each letter by 7. Also, like, remember, when you're shifting A by 2, you'll get C. And if you're going to shift Z, the last letter, by 1, you'll go back. You'll bound back to A. Right? Okay, so that is how Caesar cipher works. Now to decipher an enciphered message, you'll take the inverse shift. Okay. Again, this is a modular arithmetic system. The modulus here would be 26. Why? Because there are 26 characters in the alphabet, right? So we are going to take the modulus as 26, and to decrypt it, we are going to find the inverse shifts needed to get it back to the original position. In this case, it would be 26 minus 7, okay, right, which is 19. So if you have to get the plain text back, you will shift h by 19 and you will get a, and so on. That is Caesar cipher. I hope you guys have no doubts in the cipher. Right. We'll be moving on to the next cipher, which is Vigneer cipher. Okay. Vigneer cipher is a bit more complicated than Caesar cipher. Instead of a single shift for all the characters, it will shift each character differently according to a larger key. The key in this case would be another plain text, another plain text piece of text, and I'll show you how the shift is done. Say we have the plain text attack, okay, and we are taking a key of same size, lemon L. So what to encipher the plain text in this case, what you do is take A and you'd shift it by the first key character, which is L. How do you shift by L? You will take the index of L, modulo 26. By that I mean like L is the 11th character in the alphabet, right? So what you're going to do is you're going to shift A by 11 positions and you'd end up getting L itself. Similarly, the next character of the plain text is T, and you're going to shift it by E. When I say shift it by E, I mean shift it by 4, because E is the fourth. E is in the fourth index of in the alphabet. First index would be 0, which is A. Second index would be 1, which is B. Similarly, E is the fourth index, and so you're going to shift E by 4 positions, and you will get X. Do that with all the characters and all. You combine all the plain text with the key, and you'd get the cipher text. So right, that is Vigneer cipher. I hope you guys don't have any doubts. If you guys have any doubts, you can just post it in the comment section. Okay, so so far we discussed Caesar cipher and Vigneer cipher. These were like very basic cipher, and these could be like easily cracked because the key space is very less, as in the amount of keys you can encrypt something is very less, especially in Caesar cipher. Now we'll move on to a slightly more advanced cipher system. Okay, so now we'll look at Hill cipher. Right. I'd like to remind you guys of the same notion of how we convert between characters and numbers. We are going to need that to implement the cipher. So, we'll be mapping each character to a number modulo 26. So A will be 0, B will be 1, Z would be 25 similarly, and addition between two characters. Say you want to add A and B. You add it under like the modulus 26. So in the Hill cipher, what we do is we'll take, say, an n length. We take the data, we split it into chunks of n, and we construct a matrix, column matrix with n rows, like this, and we'll multiply this matrix with a key matrix. Suppose, say we have a 3 by 3. Say we are taking as data 3 chunks at a time, like chunks of 3 at a time. 0 to 19 would be the first 3 characters, and to get the ciphertext, you'd multiply this column matrix with this key matrix, and the result you'd transform the result, you get modulo 26. So we'll take in the remainder of the result with 26, and that would be your ciphertext. And you can convert this ciphertext back to ASCII or plain text. Now, In Hill cipher, decryption is to simply multiply with the inverse of the key matrix. So you take the encrypted result in the column matrix form, and you'd find the inverse of the key matrix and you'd multiply it, and again you'd get a column matrix, and you'd take each of the result modulo 26 to get back the plain text matrix, and you'd convert them to ASCII to get the actual plain text. Okay, so sorry for the interruption. We'll be continuing the stream. I hope I'm audible. Am I audible? Hello, am I audible? Am I audible? Okay, so we're gonna continue with the session. We talked about Hill cipher. That was Hill cipher. Hill cipher, basically you take the plain text, divide it into chunks of length n, and then you would convert it to a column matrix. Multiply this column matrix with a key matrix of n by n size. Take the result. For each element in the result, you take it modulo 26, and you convert them back to ASCII. So that's how you get the ciphertext. And to convert them back to the plain text, you take the same, like you convert the ciphertext into column matrices of size n, and you will take the inverse of the key matrix, multiply this column matrix with this inverted key matrix, take the result modulo 26 and convert it back to ASCII. That was Hill cipher. So now we'll move on to monoalphabetic substitution cipher. Simply substitution cipher. This is a simple cipher where each letter in a message is swapped with a different letter, and like the swap will stay the same for the whole message. As in, all, say for example we are swapping A with L, so then all A in the cipher in the plain text will map to L. Right. One peculiarity of substitution cipher is that since like we can perform frequency analysis on the ciphertext to get hints about the plain text, because the frequency of the plain text will stay the same for the ciphertext. It's just that the characters will be different. So the most frequent letter in the plain text, we could find out the most frequent, if you know, say the most frequent letter in the plain text, we could take the most frequent letter in the ciphertext and map it to the most frequent letter in the plain text, and you can do this mapping for each letter and get the plain text back. We'll discuss frequency analysis in more detail later. Now Rote 13 is again a different form of a cipher. It's similar to Caesar cipher in the sense that we are going to apply a shift to each of the character in the plain text. So to encrypt a message in Rote cipher, you take the plain text, you take each character from the plain text, and you shift it by 13. 13 is a shift, that's why the name Rote 13 came. And then for each character in the plain text, you shift it by 13 and you get the ciphertext. And to decrypt it, you do the same again. Just shift it by 13 back and you'll get the plain text. That is one peculiarity of Rote 13. For any other shift value, if you shift it twice, you won't get the plain text back. In Rote 13, however, if you shift the ciphertext with again, you'll get back the plain text. Okay. There are variations of this cipher, such as Rote 5 and Rote 47, in which we shift the characters by 5 and 47 respectively, but Rote 13 is the most popular one. Okay, now in the classical, in the era of classical cryptography, like Enigma machine is a very marvelous piece of invention. It was used by Nazi Germany during the World War II to send encrypted messages to its people. It worked on the basis of circuits, electromechanical circuits. So what it would do is map each character to another character through circuits, and there would be rotating disks which you could alter, which you could rotate to map a different character from the plain text to the ciphertext. So there are multiple ways to initialize an Enigma machine. The rotary things, right? If you could, before encryption, you would set values for each of the rotating disks, and that would sort of act as the key for the encryption. We have the same settings in another, let's say Enigma machine, you would be able to decrypt a message. The thing with the Enigma machine is that it was very similar to substitution, multiple substitution. Each of the rotary disks could represent a substitution, and cryptanalysis was done on this, like it was broken by almost like end of that time. Okay. Let us start with the practical session now. We discussed so far Caesar cipher, Vignia cipher, Hill cipher, and Road 13. Now it's your turn. This is a message which has been enciphered using Caesar cipher. Do try to get the message back. I'll give you a few minutes to try it, and after say 3 minutes I'll go to the solution. Okay. Okay, so I think a few minutes have passed. Did any of you guys get the solution? To find the solution, basically we use an approach called as brute force. I told you this was Caesar cipher, right? So in Caesar cipher, you could have, we are encrypting the message using a shift. But the problem is that the shifts can only be from 0 to, not 0, 1 to 25, 5, because there are only around 25 shifts possible. So we can just try each of them and see if a value matches. There is this website known as CyberSchef, which you guys can try out right now in your web browser, and just copy paste the input, this ciphertext into the CyberSchef, and select Road 13 brute force from the sidebar and see the results for yourself. For example, and you'd get the message. The message was Caesar didn't think this through. I hope at least a few of you get it, at least after the session. Okay, so now we can look into implementing Caesar ciphers on our own. To implement Caesar cipher, the algorithm is simple. You take an input string, and for each character in the string, you'd shift it with a given shift, and then you'd add this shifted letter to the output string. I'll be demonstrating this within Python. You guys can follow through. Yeah, nice. I see that one guy has got the answer. Very good. So now we're going to implement the same thing within Python. I hope you guys can see my terminal. This is the Python's live editor interface, by the way. Okay, so say my plain text is hello world. Okay, so that's my plain text. My shift value, let's say, is 3. I'm going to define a function to implement Caesar cipher. You guys can watch it. Before that, I'll show you a bit of basics. So each character in the plain text, right, it has a mapping to numbers. It's called the ASCII encoding. So to see the ASCII encoding of a character, you can just do this function, odd function, and pass the character to it. So the ASCII value of H is 72. Now, when we are working with Caesar cipher, right, we are working in the numbers in the range 0 to 25, like modulo 26. So to get that, what we can do is basically subtract the ASCII value of capital H with capital A to get like a number from the range 0 to 26. Similarly, for small letters, you can subtract that character's ASCII value with the ASCII value of small letter A to get a number in the range 0 to 26. From there, we can implement Caesar cipher easily. So, like this. So, yeah, the index of H in 0 to 25 would be 7 because it's the 8th character. Right. So, let's define a function. We'll be passing on the key, which is the shift, and we'll be passing on the plain text to it. First of all, we have to iterate through each character of the plain text and store it in an output array. So let's declare an output string for each character in plain text. We check if the character is uppercase or lowercase. And then if it is uppercase, we'll subtract the ASCII value of capital A with its ASCII value. And then apply the shift to it. And then convert it back to ASCII. So to do that, we'll add back the ASCII value of capital A, and then we use this function known as CHR to convert the number to a character. Okay, and this now that we have shifted the input plain text, the character of the plain text, we'll add it to the output result. Now, similarly for the lowercase case, we forgot a very important step here. We forgot to take the output modulo 26. That is a very important step because we want the numbers, the index of the characters to stay within 0 to 25. Right? So what we have to do is take, after applying the shift to the index of the plain text character, you take it modulo 26. So here have covered the case of capital letter and small letter. We'll just ignore all other characters which are not what you call alphabets. That's it. Let's test this function out. Wait, never mind. Okay. How many brackets? Yes. Let's say shift by 1 and the plain text is alright. That is the ciphertext. You can see that when I shifted by 1, capital H turns out to be capital I, E becomes F, L becomes M, basically the character next to it. Let's try 13. I get this value, right? Again, this is a special case of Caesar cipher. When you shift by 13, that basically becomes the road 13 cipher. And property of this is that you can just shift it by 13 again to get the plain text back. Say, don't mind the spelling. There we go. Okay. So that was Caesar cipher. Do you guys have any doubts? Okay. If you have any doubts, just post it in the comment section. There will be a Q&A session at the end. Right. Now it's your turn to try and encrypt this message with Caesar cipher and shift 13. So basically you're implementing route 13. Try this and try it out. So far we have been talking about classical cryptography. Like all the Caesar cipher, Vignes cipher, everything comes under classical cryptography. Unfortunately, all of those are, while fun to implement and work with, are not secure for actual information hiding. So in modern cryptography, you could subdivide it into encryption scheme. You could subdivide it into two. One of them is symmetric cipher and one of them is asymmetric cipher. So we talked about encrypting with a key, right? Encryption takes in a key. So in symmetric ciphers, you have a plain text, a key, and the algorithm. The algorithm would take in the plain text, the key, and output a ciphertext. Simple as that. It's exactly what we saw right now. But for asymmetric ciphers, you have two keys. One key for encryption and one key for decryption. The keys would be separate, so you can't encrypt. You can't encrypt with the decryption key and vice versa. Now, why do we need two keys? Let's imagine a scenario. Say two people needs to send a message secretly. Alice and Bob, let's say. Alice and Bob must share a key for them to encrypt a message with a symmetric cipher, because both of them needs to know the key beforehand, before the communication happens, so that they could encrypt and decrypt at each end, right? The problem with that is sharing the key would take if to be done physically, it would take a long time. There are protocols to share keys between parties, but besides this is one of the disadvantages of symmetric ciphers. It's that you must share the key between the both parties should share a same key for communication to happen. While in the case of asymmetric ciphers, you don't actually need to share a key. You can say Alice is sending a message to Bob. Alice simply needs to take Bob's public key and encrypt her message and send it to Bob, and Bob could decrypt it with his private key. An example of asymmetric cipher is RSA. In RSA, a person has two keys. One is his private key and one is his public key. He shares his public key to everyone for the duration of communication. And anyone who needs to send a message to Bob can simply take their message, encrypt it with Bob's public key, and send it to Bob, and Bob could just decrypt. An example for symmetric cipher would be AES, because it shares a single key. Both parties need to agree on the key before communication happens. When it comes to symmetric ciphers, we have two types of symmetric ciphers. One of them is block ciphers and one of them is stream ciphers. The difference being that in block ciphers, whatever data that you have to encrypt, the message, you divide it into chunks or blocks of an arbitrary length, and you encrypt, you work with each block individually. And each block will get encrypted individually and in the lead or into the cipher text. Stream ciphers, on the other hand, has no restriction on the data size. So, in the case of block ciphers, data need to be a multiple, need to be of a specific multiple of a length. Say 16. AES, the symmetric cipher. For AES to work, it should usually, for AES 128-bit version to work, the data should be of length of multiple of 16. If it's not, we'll add some padding bytes, some extra bytes to the plain text to make it a multiple of 16 and then encrypt it. That is what block ciphers do. Stream ciphers, on the other hand, has no restriction on the length of the data being taken. So we could have any arbitrary length data and it would just give out a cipher text of the same length. Okay. This is a schematic representation of how block ciphers would look like. We have the plain text, the first block of plain text P1. We take the same key, encrypt the first block, and you get the encrypted cipher text block C1. 4 different blocks. What you're seeing right now is something known as electronic codebook mode of encryption, in which each block is just encrypted separately from all the other blocks. There's no connection between the blocks. For decryption, you just take the block and decrypt it with the same key and you get the ciphertext. Now, on to stream ciphers. Stream ciphers you would actually work with on the bytes or the bits. So you have a plain text stream, the stream of plain text, and you have a cipher, a key stream. And you'd most of the stream ciphers work with XOR. Do you guys know what XOR is? How many guys here know what the XOR operation is? Have you guys heard of XOR? I believe a few students will know what XOR is. Okay, I'll explain what XOR is. So, we are looking at binary data here, right? So, data and the cipher stream both are in binary. In binary, XOR you see 2 bits here, right? 0 and 1. When you XOR 0 and 1, you'd get 1. Basically, if the bits you're XORing with are different, you'll get 1. And if the bits are same, you'll get 0 as a result. 0 and 1 would give you 1. 0 and 0 would give you 0 because both the bits are same. 1 and 1 would give you 0 because again both the bits are same. And if the bits are different, you'd get 1 as an output. So yeah, on to stream ciphers. in stream ciphers, what happens is you have a plain text stream and you have what is known as a key stream. And you XOR the key stream with the plain text stream to get the ciphertext, right? Like this, say this is a plain text is a key stream, and XOR it together to get the ciphertext. We can generate the key stream in multiple different ways, and many different algorithms use they'll usually take in a key and they'll just expand the key to the length of the plain text and then XOR them together to get the ciphertext. Okay. Right. So we are going to look at another challenge. We're going to look at repeated key XOR, a cipher system, basically encrypting a message using repeated key XOR. We'll be working in Python to do this. I'll show you the basics of how to do XOR within Python, and then you can try decrypting this message within like in your locally. I'll send this message to you in the okay. So I have posted the ciphertext. Now we will look at how to deal with actual data, bytes of data within Python. Right. I'll switch back to my terminal now. Okay. So we're back in the Python terminal. Right. Data is usually represented in say. Let's take a string in Python. I have a plain text. Hello. Currently, the data type of this string, this plain text is a string. We type it's a string. We'll be working on bytes now. Bytes is a more raw data representation. It's more of how data is stored, like in files and stuff. Everything is bytes, right? We'll work with raw bytes in this session. So to convert a string data type to bytes, just do .encode. Say plain text .encode, and you'd get the bytes. Just B here just means that this is bytes. That's all. That's just a this is a notation to represent that the string is a byte string. Okay. So to access each character from the byte, right? Do you guys have any doubts regarding this? If you guys have any doubts in what I have told so far, just post it in the comment section. Okay, so right, we had a string here, hello. We converted that to a byte string by doing .encode on the string. So you have a byte string here. To access each character in this byte string, right, you just do indexing. So if I want to access the first character, I'll do let me convert this to byte string. Say I want to take the first character, I'll just do plain text of 0. Now what you're seeing right now is a representation of H in ASCII. H is capital H would be 72 in ASCII, that's why you're getting 72. So in Python, if you access like each byte by the index, you'd actually get a number back, not the byte string. Okay, which makes it easier to work with bytes. So now we want to like, how do you XOR two pieces of text together? Say I have my plain text is hello. Say my key is A, B, C, D, E. Okay, this is again another byte string. So I want to XOR the plain text with my key. What I would do is for each character. I'd use a Python function known as zip. What zip does is it basically takes in for, say, I'll give you an example. For a character key in zip, right? What it does is basically takes in the first, right? Wait, I see that a person has already cracked the thing, but very good. For others, I'll just show this thing. What this zip function does is basically it takes in each byte of the plain text and key together. So you'll take the first byte of the plain text and the first byte of the key together, then the second byte of the plain text and the second byte of the key, like that. So to XOR them together, we'll just do character of character XOR K. The up arrow is the symbol for XOR, and then you could convert them back to text using the CHR function. You're seeing empty spaces because you can't actually the CHR function only converts numbers to ASCII, not bytes. So to convert a number to a byte, you do bytes. This is a notation of how you do it, right? So now currently on the screen you can see how the output would look like if you XORed a plain text byte with a key byte. To recap, a byte has values. A byte could hold 256 values, right? So we saw that for the plain text H, capital H, the value was 72, right? Similarly, when you go above 128 in the range of byte, you will see some unprintable characters and stuff. Python will print them in a different notation for us to understand easily. Right. To implement repeated key XOR, you could just do. You could cycle. Like what you need to do is basically you need to cycle through the key. So you have the message here, right? You take in the first character of the key K, XOR the first character of the plain text with the key character K. For the second character of the plain text, you XOR it with the second letter of the key E, Y, K, E, Y, and so on and so forth. Basically, you're repeating the key. So you'll first take K, E, Y, XOR the first three characters with that, the next three characters with key, the next three characters with key, and so on and so forth. I showed you the basics of how to work with bytes in Python, and I see that one guy has already posted an answer in YouTube. Do try this challenge out, and that's the end of the session. Now we can have a question and answer session. If you guys have any doubts, anything, any doubts in anything that I've discussed so far, just post it in the comment section and I'll reply to you. I'll go through the slides once again if you right. So if you guys felt any technical disturbance, like there were a few technical issues, and if you guys feel that I need to rephrase something that you guys didn't understand any topic, you can just ask for it, and I'll be here to explain it. I'll go through the slides once more to see like what was covered. We covered what was encryption. Encryption is the process of taking in plain text. You have a key. With the key, you convert the plain text to a cryptic form such that you can't revert it unless you have a key. We discussed the difference between encoding, encryption, and steganography. We saw some classical cipher examples, and we talked about modular algebra. Like modular arithmetic is a very fundamental concept which will help you understand some of these classical cryptographical cipher systems better. If you guys have any doubt on this, please do tell. We looked at Caesar cipher, where you shift each character by an amount. We looked at Vignia cipher. We looked at Hill cipher, substitution cipher, Route 13, the Enigma machine. We talked about the Enigma machine, and we had a few challenges. Alright, that would be it for the session. I'm gonna end the session now. Thank you all for attending.